So as the name implies, probability generating function is much more useful in computing or obtaining the PMF from the generating function. But it's also useful if you need the moments instead of the distribution. Maybe not as useful as moment generating or characteristic function, but it is also possible to obtain the moments from the probability generating function. Again, just write this uh, as the definition implies, put in this summation, and if you differentiate it, you have this. The PMF value here multiplied by k times z to the power k minus 1. So if you evaluate this at z equals 1, you see, this term will go away. It will be just 1. Okay, so you will have just this sum from 0 to infinity, k weighted by the PMF value at k. So by definition, this is the expected value. Therefore, this is how you obtain the mean of random variable x from its generating function. You differentiate it with respect to z and then evaluate it at z equals 1. You see, it's also useful generating function. You can obtain the moments from it. And if you differentiate it twice, let's see what happens. Okay, differentiate it twice and evaluate it one, you get the derivative of this expression here, because this was the first derivative, and therefore you will have k times k minus 1 times z to the power k minus 2 weighted by the PMF value. Okay, and if you evaluate it at z equals 1, z to the power k minus 2 term will disappear, and what you have is this, k times k minus 1 times the PMF value. Okay, if you arrange the terms, you will have k squared times the PMF minus k times the PMF. Okay, if you sum this and sum this term will be the second moment, and this term will be the mean. So the second moment minus mean equals this quantity here. Okay, therefore you can actually obtain the variance using these two, because if you remember, well, variance is equal to the second moment minus square of the mean. Okay, so here I have the second moment minus mean, and here I have the mean. Therefore, this is the second moment. This quantity, the second derivative evaluated at 1, plus this, the mean, the first derivative of the generating function evaluated at 1, you have second moment here, minus square of the mean, right? This. We have a square here, okay? So this is the mean square. So you have variance in this way. And in general, if you just look at this expression, let me clear this page. Okay. So here, you see, we have, this is the first derivative. If you apply to this if you multiply this by z, you get the sum from k equals 0 to infinity, the PMF times k times z to the power k. Okay, so that is z times the derivative. If you differentiate it once more, what you have is, since you will have k here, you will have now k squared z to the power k minus 1, the PMF, and the sum. Okay, and then multiply it again by z, so you get z to the power k here. So when you repeat this n times, okay, differentiate, multiply by z, differentiate, multiply by z, differentiate, multiply by z, repeat this n times, okay, and then evaluate it at z equals 1. That's how you obtain the nth moment from the generating function. Okay, if you do not multiply by z every round after every differentiation, what happens is the nth derivative with respect to z evaluated at 1, instead of k times k times k times k k k, you get k times k minus 1, k minus 2, k minus 3, etc. up to k minus n plus 1. So this is what we call a factorial moment. Okay, this is a falling factorial. And this is like x times x minus 1, x minus 2, dot, 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 x minus x minus n plus 1. Okay, this is the expected value of this quantity. Okay, so this is how you compute moments and related statistics using probability generating function.